So here we discuss the frequency domain representation of continuous time signals. This representation or analysis helps us in understanding the different concepts related to the communication, such as the modulation and demodulation of signals. So the first thing that we'll look into is Fourier series. So Fourier series is to represent periodic signal in terms of complex exponentials as a sum of complex exponentials. So what are complex exponentials? So this e raised power j n omega naught t represents a set of complex exponentials. The set depends upon the values of n. They can be from 0 up to plus minus infinity. So this now these set of exponentials are orthogonal over any interval of duration, which means that if we have e raised power j m omega naught t multiplied by e raised power j n omega naught t, and the product of these two when integrated over one time period t naught will give us a value of 0 if these m and n are different, and this will give us a value of t naught, the time period, if the m and n are same. So this figure shows some exponential terms. This basically shows the real part of complex exponential. So as we'll see later, there is a the imaginary part as well. So when they are combined, we get the combined exponential signal. So this shows that the product of two cosines that have a different frequency. So the 4 pi x is the frequency of 4 pi x is 2 times the 2 pi x, and so the product is shown in the shaded region, right? So this is how we can imagine the product of two cosines or complex exponentials. Now a signal gt can be expressed over an interval of duration t naught, which is in t naught is in time, it's in seconds, and it can be represented as an exponential Fourier series. So as we said, gt is, let's say, a periodic signal. This is the exponential Fourier series in terms of which we represent gt. So the idea of representing any signal gt in terms of complex exponentials is because these exponentials, they are generally easy to process. So if we have to process a signal gt, then it becomes quite complex because it can have any shape. The complex, if we write it in terms of complex exponentials, so for example, we want to take the derivative of gt, then if we take the derivative of this side, so we know that the derivative of exponential quantity is the same exponential quantity multiplied by only a certain number. So effectively we can convert derivation into simple multiplication. So this is the significance of writing any signal gt in terms of a sum of complex exponentials. So the next task is to determine the contribution of each complex exponential in this sum. So that can be done by using the formula dn. So this represents the coefficient or the contribution of each complex exponential. It is determined by taking the integral over one time period of gt and the another complex exponential e raised power minus j n omega naught t or n 2 by f naught t. So this is the significance of the Fourier series. The exponential Fourier series above is periodic over period t naught, which is this, and consists of components of the form e raised power j n 2 pi f naught t, where n varies from minus infinity to plus infinity. So an example here, we have phi t as the signal. So this can be represented as it's a periodic signal. The period is from 0 to pi. So this can be represented as the sum of complex exponentials. The expression for this region is e raised power minus t by 2. So if we substitute these values in this Fourier series expression, so first we determine dn and then we substitute it into this summation, we get a series of terms where we can see the complex exponential terms. So when they are added, they should give us a very good approximation of this signal. Since the terms are infinite, so we cannot include, generally we have to ignore some of the very higher order terms. So we will not get an exact signal phi t, but a very close approximation of phi t. So in the exponential spectra that we will see, we plot coefficients dn as a function of omega. But since dn is complex, in general we need two plots. So one is the amplitude plot of dn. This dn is the coefficient or contribution of each complex exponential, and so one is the amplitude and one is the angle of dn. So this requires that the coefficients dn can be expressed in polar form. So in polar form we have the magnitude, and the exponential term has the phase angle. So for a real periodic signal, we know that the twin coefficients dn and d minus n are conjugates. So this can be proved by substituting the values. Even in the formula, if we substitute n, replace n with minus n, so we'll see that for a real periodic signal, this will give us the same value of the coefficient. Similarly, the angle of dn is theta n, and the angle of d minus n is minus theta n. So which means that we know that dn is equal to this coefficient and the exponential term. D minus n is the coefficient or the contribution, and e to the power minus j theta n. Right, so this relation is true specifically for periodic signals only. The spectrum of that particular signal example is drawn here. You can see the maximum contribution is from the zero frequency term or the DC term. This is because if you see the average value of this signal is high, there is no there is no negative term, negative cycle. So this has a strong DC term which can be seen in the spectrum, and the first and second order, in fact fourth order. So because the 1 and 3 and minus 1 minus 3, so the odd indexed coefficients are they are not there, and we only have the even indexed coefficients d2, d4, d6 and so on, right? So we can also plot the phase angle of this. So we have omega on this axis and phase is plotted on the y-axis. So this is the angle of dn. So this is what it means by the the Fourier series of a periodic signal. Now we can see here on this axis we have negative values. On this axis as well we have negative values. So that seems to show that we have some kind of negative frequency in these signals. So this is explained in the next slide here. So do we have negative frequency? So how do we explain that phenomena? So this can be explained by looking at the trigonometric identity. So for example, cos of minus omega naught t plus theta gives us cos of omega naught t minus theta. So here minus omega naught and plus omega naught are in the same equation. So this shows that the angular frequency of a sinusoid, this minus omega naught, is actually omega naught. The magnitude still remains the same, and it's always a positive quantity. So the concept of frequency for a real valued sinusoid describes only the rate of sinusoidal variation without addressing the direction of the variation. So when we see omega naught, if we have a real valued term, let's say here cos of theta or cos of omega naught, it does not give us, it tells us the value of the frequency, but it does not tell us the direction of rotation of the phasor due to which this frequency is generated, or due to which this cosine signal is generated. So because real valued sinusoids do not contain information on the direction of the variation, so to include the direction of variation, we have to write it as a complex sinusoid like this. So in the example, we had complex sinusoids that had cosine term plus, so the real term, and an imaginary term, so that could be plus minus j sine omega naught t. So this relationship clearly shows that either positive or negative omega leads to periodic variation of the same rate, right? So the rate is same, omega naught. However, the resulting complex signals are not the same, right? For positive frequency, the exponential sinusoid rotates clockwise, while for the negative frequency, the exponential sinusoid rotates, sorry, for positive, it's counterclockwise, for negative, it's clockwise. This can be understood by looking at this plot. So you can see there is a spiral in the rotating in this direction. On the real part is plotted the projection of this spiral on this axis. The red one shows the real part, and the projection on this axis will give us the imaginary part. So this spiral exists in both it's a complex term, and it has the real, the red one, and the imaginary, the green one. So if it is rotating like this, right, so this is one rotation direction. Even if it's rotating in the opposite direction, so let's say it's rotating in this direction, you will still get the same cause and sine, but in the expression here, plus will be converted to minus. So this is the understanding of the negative frequency concept. So then again we can have the Fourier transform of a square signal. So we can see time is on the x-axis, we have wt as the square signal. So this is the expression for the Fourier series. We need to determine dn from the expression that we saw earlier. So if we use that expression, we get these values of dn. So d naught, which means the contribution of dc term, where omega is 0, is half. So that's because you can see all of the pulses are on the positive axis, so the average value of this signal will exist. So the average value is half for one time period. Then for dn we have this expression. So the coefficients other than n is equal to 0 are shown here when we substitute values of n 1 2 3. So this is for 1 2 3 and so on, minus 1 minus 2 minus 3. So we see the plot for dn here. Now since this is a real quantity, it does not have any phase, so we will not get any phase plot for this. All of these terms, all of these exponentials are in phase, they have the same phase, so that's why the phase term does not appear here, right? So we can again have the Fourier series of periodic impulse signals. So we have impulses that are periodically repeating. So let's say we take this impulse to determine the Fourier series. We substitute values of we find dn by substituting value in this formula that we discussed earlier. So this is that formula, and when we substitute the values in that, we will see that we get impulses 1 over t naught. So we get constant amplitude signals that we have here, and delta t naught is plotted here. So we can see this is the Fourier series. So this dn is substituted, the 1 over t naught is showing here, and this is the plot of that Fourier series coefficients. They repeat at 0, omega naught, 2 omega naught, and so on, right? So then we have the some more some more information about the Fourier series. So it's about Parseval's theorem. So the theorem suggests, it says that the energy that we determine in the time domain, the energy for gt, this can also be determined, energy or power, this can also be determined in the frequency domain by summing the amplitudes of the square amplitudes of the exponential signal coefficients. So for real signal, since we know these dn and minus dn are the same, So from we can the summation can start from 1 and go up to infinity, and the d naught square can be separated, so n is equal to 0 is written here, and we have a 2 here, so it's even. So this is the most general relation. This can be used for both the cases, real or complex values of dn, right? So this is the Parseval's relation, which says that the energy can or power can be determined in time or in the frequency domain from the coefficients, right? So then this was discussion about the periodic signals, for which we have Fourier series, and then we have generally we have aperiodic signals. Let's say my voice, or some kind of music, that is an aperiodic signal, and it does not repeat after regular intervals of time t naught. So for that we have Fourier integral. Fourier integral is represented by this expression, so we write it as gf is the Fourier of gt, and gt is the inverse Fourier of gf. So these are the Fourier transform pairs. Gf is simply determined by the integral of gt with e to the power minus g omega naught t. The product of this is integrated over the minus infinity to infinity. This is how Fourier transform is determined of gt. The inverse transform is we substitute gf here and we multiply it with e to the power j omega t, and we take the integral over the frequency minus infinity to plus infinity. So this is known as the Fourier integral. We Since GF is complex, the Fourier transform, we have both amplitude and angle in this way. So from the Fourier transform pair, we can see if we replace f with minus f, so what happens here is the minus here disappears, so it becomes plus. And if in this case gt is a real function, so that means this g minus f, and this g minus f is equal to gf conjugate. So we get the same result, this result, if we take conjugate of gf. So this minus will become plus, so it is the same as if we have replaced f with minus f. So replacing f with minus f means that we are reversing the gf. So these are just some relations that are good to know. So the magnitudes of both these terms are the same. The angle, the phase angles, however, so they follow the even symmetry. The phase angle follows the odd function symmetry. So if you replace minus f in theta, it becomes minus theta f, right? So for real gt, amplitude spectrum gf is an even function, as we can see from this expression. The phase spectrum is an odd function, as we can see from this expression. Then Fourier transform is of an important signal is the rectangular signal. We can see here it's denoted by this rect signal. So for example, this is a rectangular signal. We have another rectangular signal which is in terms of tau. So unit rectangular pulse is shown here. It has been expanded by a factor of tau, as you can see here. So this can be expressed as rect x by tau. Denominator is the width of the pulse. So here this tau represents the width of the pulse. So we have minus t by 2 up to plus t by 2. The total width is minus tau by 2 to plus tau by 2. The total width is tau. We have the Fourier transform of this rectangular signal. If we determine it by substituting the values in the integral, we will get a sinc function. So the relation between the rectangular and sinc function is shown here. This is an important relation and generally used at different stages of the the communication system course. So there is a duality that exists between time and frequency. So if in time domain we have rectangle, we will get a sinc in the frequency domain. If in time domain we have sinc, we will get a rectangle in the frequency domain. So this can be proved by substituting values in the Fourier transform integral. Then we have the time scaling property. So if we scale the time, let's say we multiply it with a constant a, then that means we divide the frequency by f by a. So we change the variable f into to f by a, and also the amplitude is changed by 1 over a. Now the time scaling property states that the time compression of a signal results in its spectral expansion. So here you can see if the time is compressed means that, for example, a is 2, it's a positive quantity, then we will see expansion in the frequency domain. So if a is positive, that means we are compressing it by expansion. From this, it does not look like we are getting an expansion, but the way we get expansion is that now the the axis, the steps on the frequency axis are smaller, but the overall signal width is large. So the bandwidth of a signal is inversely proportional to the signal duration or width. Now if the width of the signal is large in the frequency domain, its width in the time domain will be narrow, right? So this is how it works. So then we have the time shifting property, which means if we have gt, its Fourier transform is gf. If we delay or forward the gt, if there is a shift in time, that will appear as an exponential term in the frequency domain. So this exponential term, so in other words, the Fourier transform will be phase shifted. So all the terms in the Fourier transforms will be phase shifted by this amount, because this term will be multiplied with all the terms in the Fourier transform. So here we have an example. This red plot is the unshifted version. Delay means that we t minus t naught means that, let's say we have delayed it, and the delayed version is shown as the green plot. So there is a delay of, let's say, 2.305 millisecond, which means that if we, for example, observe the phase at this point, so the phase of this term, the green and red one, at any instant of time t is it is now changed. So delay in time shows a phase difference in the frequency domain. This can be visualized as well from this plot. So in summary, we have seen the exponential Fourier series. We have discussed Fourier series calculation of some important signals. Then we discussed Fourier transform of aperiodic signals, and we discussed the Fourier transform of some important signals. And then we discussed the properties of Fourier transform.